Hello everyone! Welcome to another lecture for interactive computer graphics. Today we're going to talk about textures. Actually, this whole week we're going to talk about textures. Remember, I've been telling you last week that we're coming close to the sort of overlap between the Introduction to Computer Graphics course and Interactive Computer course, that is this course. This week is going to do it. So this week is going to be another week with substantial amount of overlap, but that will be the end of it. We're going to talk about textures, and we did talk about textures in the Introduction to Computer Graphics course. So those of you who have taken that course, you'll see that there's going to be quite a bit of overlap, especially today. Next time on Thursday, I'm going to talk about how to handle textures on the GPU. And that's going to be a little bit different because that's going to be in the context of OpenGL as opposed to WebGL, is what we did for Introduction to Computer Graphics. All right, so I'm going to dive in and talk about textures today. Actually, I'm going to add a few more details about textures. That's not going to be stuff that we extensively talked about in the Introduction to Computer Graphics course. Okay, so today's topic, textures. What are textures? What do we do? What do we use textures for? Well, when you say texture to someone who's been doing computer graphics, they will probably think that you're talking about an image, something like this, that you will figure out a way to put on an object like this, right? So this is our 3D object, and that's my texture. I'm going to take that texture, and I'm going to somehow put that texture on that model, right? And it will hopefully look like this. So as you can imagine, there are various ways of doing this. I mean, I can take this texture and just stick it on this model in various different ways, right? I can, for example, I can just take it and just place it on one side like this. If I do that, as you can see that the sides are sort of using the same column of pixels everywhere. You see that? So yeah, on this side things are looking fine, but this side over here doesn't look like, it's not quite what I would like it to look like, but maybe that's what I want. If this is what I want, then it's okay. But if this is not what I want, if I want to see this texture sort of repeated on every face of the cube, maybe I should map it like this. I could take the same texture and attach it from different directions. So based on the direction of the surface normal, I can figure out which one of these I use. Another more standard way of doing this would be what we call cylindrical mapping. So you take, you basically form a cylinder around the model, and that's how you define what pixels of this texture image will correspond to what part of the 3D surface. You could also have these caps on either end. All right, so this is cylindrical mapping. I wrapped the cylinder. There are other ways, of course. Now this one may look familiar. Spherical mapping. So this is more or less what we do, for example, when we're trying to draw a map of the Earth, right? So when you look at a map will look like this, right? But it's actually a map of the Earth. So you can imagine this as you take that map and you wrap it around the sphere that is our globe. So that would be spherical mapping. So there's going to be what we call a seam around here. You see that this is a seam where the two ends come together. Two ends of the texture come together. Seams are oftentimes not desirable and they can give you trouble, so maybe because of that you don't like it. But another thing that's not so nice here is that we have quite a bit of stretching of that texture. So over here, like the top parts of that texture correspond to a very small surface here. Same goes for the bottom side here. North Pole and South Pole, where things are compressing to all the way to a single point. Around the equator, things are as stretched as they could be, right? So the same amount of area on this map does not correspond to the same amount of area on the sphere, which is a practical problem for applying textures to surfaces, right? Because if I have enough image resolution here, if I have enough image resolution near the poles, then I'm not going to have enough resolution near the equator. If I have enough resolution near the equator, I'm probably going to have too much resolution near the poles, right? So that stretching is something quite undesirable. But the other undesirable thing here is this seam, where the edges of the texture, the two edges, like this edge and the other edge on the other side, they come together over here along the seam. And that's also undesirable because if the colors, if the texture data on either side of that seam, they don't match, then the seam is going to be visible in my final rendering, which is not going to be very nice. One way of getting rid of the seam, or at least minimizing it as much as possible, is using a different kind of mapping, the shrink wrap mapping, where all of the edges of this texture come together at one point here. So the seam collapses to a single point. It still has to exist somewhere, but at least it just happens at a single point. And depending on your scene or how you present this object, you might be able to hide this seam. But then you have quite a bit of excessive stretching here, right? So all the edges collapse to a single point. So you're going to have maybe too much resolution around here. On the other end, you're going to have probably not enough resolution. Or if you have enough resolution on the other side over here, then you're definitely going to have too much resolution, too many pixels, too many texture pixels down here. So yeah, that's another way of doing this. So, but typically the way we do mapping is not one of these simple functions. These are relatively simple functions for mapping. Typically what we do, what we use for mapping is that we take an object and we split it into a bunch of pieces. And then we try to map each one of these pieces separately. So that becomes, so basically mapping a texture on a surface becomes a much more difficult process, especially if you don't have simple shapes like a sphere. Mapping is a much harder problem. And that brings us to texture mapping. So texture mapping is the idea that some sort of mapping is defined, and then we're just going to use that mapping. So there are lots of components to texture mapping, but the component that is going to be important for us in the context of rendering or interactive rendering on the GPU is going to be about using this mapping, not generating this mapping. So here's what I mean. So what I want to do is I want to take a texture and figure out a way to map it onto this object, right? But actually, texture mapping does the exact opposite. It takes the object and maps it onto the texture. Okay, it's more or less the same thing, sort of, not exactly. There's an important distinction here. That is, this is not necessarily one-to-one mapping, right? Not every pixel of my texture corresponds to a position on the object, but every position on the object must correspond to a position on the texture space. Right, so mapping is actually this way. So the way we're going to define this mapping is that for each triangle, I'm going to have a corresponding position for that triangle in texture space. Now, how exactly this texture space position is defined, it's not going to be our concern. So we're going to assume that somebody went through the trouble of taking every triangle here and figuring out where it falls on the texture space. Now, for simple objects, and this teapot is a relatively simple object. For simple objects, this is quite easy, not very difficult to do. But for general objects, this can be a very, very, very complicated and painstaking process. People spend a lot of time, a lot of energy manually mapping these triangles. I mean, of course, they don't take every triangle and place it on the other side one by one. They probably get groups of triangles, and they use some software that can automate this process, or at least semi-automate parts of this process. But oftentimes there is a lot of manual intervention going on here. So an artist would actually take an object like this and figure out how this object should be nicely mapped onto this texture space. So this is a lot of work, a lot of manual work, and I'm emphasizing this because I would like you to sort of appreciate all the effort whoever prepared the model had to go through to prepare this for you so you can actually use it for rendering. The nice thing here is that once someone goes through the trouble of defining this mapping, then it's all set. So once I know where each triangle goes in texture space, then I don't need to worry about how this was defined. If that's someone did this manually or someone used an automated algorithm, I don't care. Whatever they used, at the end, I have this definition. Each triangle has a well-defined position in texture space. That's what's important in the context of rendering. The way this is going to be defined is that for each vertex here in the object space, I'm going to have a corresponding position in texture space, right? For this red vertex corresponds to there, this green vertex corresponds to over here, and this blue vertex goes over there, right? And all these positions in object space are vectors, so they live in the object space, right? So this is the coordinate frame of the object space. Similarly, in the texture space, I'm going to have a coordinate frame as well. So this is going to be the bottom left over here is going to be the origin. That's the OpenGL standard. It's not the top left. It's the bottom left. That's the OpenGL standard. And I'm going to have two directions here. U direction is going to be like the horizontal direction, and V direction is going to be the vertical direction. All right. So for each position here in the object space that's represented by a 3D vector that's with XYZ coordinates, I'm going to have a corresponding vector in 2D that's going to be in this UV space with U and V coordinates. Okay, so you can think about this as each vertex having a texture coordinate attribute. All right, so it is its position in object space, and this is its position in texture space or its texture coordinate. All right, and using that, we will be able to access textures on the GPU while we're rendering. All right, so I'm going to talk about how to set this up and how to access everything while rendering, but I just want to mention this briefly. So we're going to be using textures in the fragment shader, and actually what we're going to be doing is that we're going to be specifying our material properties using textures. For example, our diffuse color can come from a texture. Our specular color can come from a texture, right? So all of these material properties that we've been using for shading, they can be defined by a texture. So I don't have to have the same color over the entire surface, same diffuse color over the entire surface. That diffuse color may be defined by a texture such that the diffuse color changes on the surface, right? Just this is exactly what's happening here. I have a diffuse color that's defined by this texture, right? And the GPU will help us use these textures quite a bit, actually. And I'm going to talk about today what happens under the hood. And then next time we're going to talk about actually how to set it up. So what happens is that, I'm in my fragment shader, I am getting a bunch of fragments for each triangle, right? More specifically, I am getting the center coordinates of each one of these fragments. So let's take a look at one of them. Let's say this point, let's say my fragment shader received this point, one execution of the fragment shader and received that point. So obviously the position at that point is defined by these three vertices. In whatever space I specify these three vertex positions, my fragment shader is going to get the interpolated position here. Similarly, with the texture coordinate attribute, if I send the texture coordinate attributes from my vertex shader, my fragment shader is going to get this interpolated texture coordinate from the rasterizer, right? And that interpolation is, of course, using the birth-centered coordinates of that point. So same thing as always. So let's take a look at what happens in texture space. So this is the position. That position corresponds to a particular position in texture space. And what we're going to have to do is to figure out the value of the texture at this position. Now, if you haven't faced with this problem before, you may think that this is relatively simple. Actually, it isn't. It's actually a relatively complicated thing, and I'm going to talk about that right now, right? So let's talk about texture sampling, otherwise known as texture filtering. That's going to be the operation of reading the color of a texture at any given point. All right, so here it is, my lovely texture. Let's say this is my texture that I'm going to be using. I'm going to be sampling this texture, all right? So this is a very low resolution texture. As you can see, it's just an 8x8 image, not something particularly interesting. Well, of course, pixels, remember, are not little squares, right? Pixels are actually points and values at the centers of those positions. So pixels are actually values at certain positions, in this case, texture space. So for texture, we call those pixels texels, so each one of them are texels, and they represent a value at a particular point, and that's very important. It's very important to think about texels as point samples in the texture space, right? So I know the value of this texture at these positions, but if I'm given a random position in texture space, like let's say this one, right? This one does not correspond to any of my texels directly. So I need to figure out a way to compute the color exactly at this point, right? So the simplest thing I can do, what is it? The simplest thing is just look at the nearest one, look at the closest one and use that. And in that case, if you think about it this way, if you use this, what we call nearest filtering, it will look like my texels have this square shapes, because within a square around each one of these texels, I'm going to have the same color, right? So in each one of these squares, the nearest texel is going to be the one at the center here. So my texture, when I render it, will look very much like this. All right? So that's going to be nearest filtering, but of course, I'm just picking the closest value. I'm not treating my pixels as little squares, my texels as little squares. All right, so this is nearest filtering. One step better, we can do something slightly better. We can use what's called linear filtering, right? So with linear filtering, more specifically, it's bilinear filtering, because it's linear filtering in 2 dimensions. So what we're going to do with bilinear filtering is that we're going to take a look at the 4 closest texels, not just the one closest, but we're going to look at the 4 ones that are around the point that we're trying to compute, this point. All right. So let's get rid of all of the other texels and just let's concentrate on these 4 that are the closest. And I'm going to blow it up a little bit. All right. So what we're going to do is that I have these 4 values around it, and I'm going to have to figure out a way of interpolating these 4 values to compute the value here. That's what I'm going to try to do. So I'm going to interpolate the texture values defined at these 4 corners. So let's draw a box that connects them. Now, look, this is not the pixel-shaped box, right? The pixels will be like, if you draw pixels as boxes, so this is going to be a box around this one, and there's going to be another box around this one. So this is this box does not quite look like a pixel. It's sort of shifted a little bit. All right. So I just connected these points, and what I want to do is to interpolate the color values, texture values defined at these points. Let's name them C0, C1, C2, C3, okay? And I would like to know the value here. Let's call that C. And I'm going to do that using bilinear filtering. So here's how it's defined. So bilinear filtering is going to do multiple linear interpolations. So let's do the first linear interpolation. And it's going to depend on the distance of this point in the horizontal direction. Now, if the size of this one edge is just 1 unit, and if this is S, the horizontal distance is S, this side is going to be 1 minus S, right? So I can interpolate these two values, C0 and C1, to find the value in the middle here, over here at that point, using linear interpolation like this. So C0 is multiplied by this one, and C1 is multiplied by this length, right? C0 is multiplied by 1 minus S, and C1 is multiplied by S. Now I can do the same thing up here to compute that value, which is going to be this, again, linear interpolation. And then now I know, now I did the linear interpolation in the horizontal direction. Now I'm going to do another linear interpolation, but now this time I'm going to do that in the vertical direction, right? So if this is t and this is 1 minus t, then I can interpolate these two values, this one and that one, using this formula, right? So this one is multiplied by 1 minus t, and this one is multiplied by t. Okay, linear interpolation, and in the end, I got my value here. Of course, I don't have to do this as 3 linear interpolations like this. I can just combine all of this into a single bilinear interpolation, and that's going to be just one formula for everything. Basically, just take these and put them in the equation over here, and it will look like this, right? So this is the bilinear interpolation formula. All right, so there's something interesting here that I want to point out. So when we're doing linear interpolation, remember how what we're multiplying a value corresponds to the length on the other side? So in this case, in bilinear case, it's going to be the area. So C3 is multiplied by the area on the opposite side. That's S times T. Is that right? Yes, C3 is multiplied by S times T, right? So C0 is multiplied by this area over here, right? So it's going to be 1 minus S, 1 minus T. Right? C0 is multiplied by 1 minus T, 1 minus S, right? And same goes for C1 and C2. They're multiplied by the opposite areas. All right, so this is what we did with bilinear interpolation. Is that any good? Or is it any better? Let's see. Let's compare nearest versus bilinear filtering. So this is a low resolution texture rendered using, filtered using nearest filtering, and the same texture, in this case I'm displaying it using bilinear filtering. It's the same amount of data, right? But still, with bilinear filtering, things are looking a little bit smoother, because in the nearest case, I'm just picking the closest textile value. In the bilinear case, I'm interpolating the closest 4 values. Of course, bilinear filtering is not necessarily the best we can do. We can do better things. For example, we can do bicubic. Bicubic would do an interpolation of values in a 4x4 neighborhood. So it's going to use a higher order interpolation. More specifically, it's going to use a cubic function to do the interpolation. I'm not going to get into the details of bicubic because, the current GPUs don't really support that. We can only do bilinear filtering with current GPUs. But for high quality offline rendering, you might want to use bicubic filtering. Can we do better than bicubic? You think? Maybe. Maybe we can get something magical like this? Well, not quite. If you want to get something that will look like this, you need more data, right? Just by using the available data here, we cannot reproduce this image. So we could use a higher order interpolation, but it's not going to give us this. So this requires using more data. In that sense, bicubic is somewhat better than bilinear. This has been known for quite some time. But bilinear is good enough if you have enough data. If you have enough data, then you can just use bilinear. It's good enough. The advantage of bicubic comes into play when you really don't have enough data. So what do I mean by enough data? What makes it enough anyway? So if I'm rendering a teapot, and let's say this is my texture, this is quite literally my texture, but anyhow, let's say this is the texture that I'm using for rendering this teapot. And as you can see, it's kind of blurry, right? So it doesn't look doesn't look all that good. It looks like I don't have enough data. So if I want to render something like this, probably I should use a texture that has higher resolution, right? So if I use a texture like this with higher resolution, now there's a lot more detail. Now I have more details of the surface, and it's not looking blurry. So the bilinear interpolation is pretty much hidden. I'm still using bilinear interpolation here, but you can't see it because all the texels are really tiny, right? But if I'm looking at this from a distance, whoa, went far away. If I'm looking at it from a distance, now in this case, I'm using too many texels, so that my texture resolution is a little too much, right? I mean, it's totally unnecessary. So, I mean, when it's close, yeah, I'm seeing all that detail and it's good, but when I stand it away and it's away from the camera and the object is really small, all the texels are tiny, then I'm using the resolution is too much. Well, is that a problem? Well, I'm sort of wasting memory, not just memory for storage, but also memory bandwidth by accessing the texture data while I'm rendering. So it's rendering this when you use a high resolution texture is more expensive than it has to be. But there is one more, much more important problem. For example, if I'm rendering a flat surface like this one, as you can see, I have this nice filtering going on and everything looks nice, right? Everything looks nice because even though the title says bilinear filtering, this isn't. This is not bilinear filtering. Because if you use bilinear filtering, this is not what it looks like. It actually looks like this. How do you like this one? It's flickering a little bit, right? Hopefully you can see this flickering with your internet connection. This video compression sometimes hides these sort of flickering stuff. But in this case, I don't think video compression will save you. Even with streamed video, you should be able to see this really gross flickering. So, this is really distracting, right? So when you have a 3D scene and you're looking at something like this, I just want to draw a flat plane on the floor. And what I'm getting is these dancing pixels, which is really not what we want. This looks really terrible. And very distracting too. We definitely figure out a way to get rid of this. But to be able to get rid of this, we need to understand why bilinear filtering would produce something that looks like this. Why would that happen? All right, so let's start with our texture. All right, so what I'm doing is, let's say that I'm taking this texture and I'm just putting it on a plane, on a 3D plane, and it looks like this, right? So I'm gonna have my camera and I'm going to look at this plane from a particular direction. Let's say I'm looking at it from this direction, and let's say that this is the image that I am generating. So I'm going to be rendering this image. All right, so if I render a high resolution image like this, it's kind of difficult to see what's going on. So let's take a look at it in the context of rendering a very low resolution image, so we can see the pixels nicely. Right. So let's say that the low resolution image I'm rendering has pixels of this size. Of course, again, pixels are not little squares, right? So what I'm going to be rendering is going to be the samples at the centers of these pixels. So that's what I'm actually rendering. Right. And what I'm going to be doing is I'm going to be computing the value. I'm going to be doing shading and rendering. Let's forget about shading for the time being. Let's say that I'm just looking at the texture value and outputting the texture value in my fragment shader, right? So what I'm going to be outputting with bilinear filtering is going to be the value that corresponds to the center of each pixel, right? So I'm going to be outputting these values. Let's concentrate on one of these pixels here. Let's concentrate on that one. All good? So that position on this texture corresponds to that quite little gray area, right? So this pixel if I just use the value of the texture at that point, that pixel is going to take the color gray, this color, which is okay. I mean, that's what that point corresponded to, so it kind of makes sense. But what happens if I take this plane in the background and just move it slightly? Just let me move it slightly. Oh, what happened? Did you see that? I moved just a little bit. I took this, I moved it. You see that? Just a little bit motion. With just a little bit motion, now the center of that pixel corresponds to a part of a brick. And that brick has that color at that point. So imagine an animation going on. In one frame, this is the color that I was getting. In the next frame, I'm getting this color, right? So I get this color and then this color, this color and then this color. So as you can see, the color is just rapidly changing from one thing to something completely different. And that's exactly what was going on in that example that I showed you. And that's why we had all these dancing pixels that were sort of further away from the camera, because the probability of something like this happening is a lot higher when you're looking at an object from far away and then the texture has high resolution. What I want is not this or this. What I want is this average color that corresponds to that entire pixel area. So I would like to know what I would like to use for that pixel is this average color that corresponds to that entire texture area that corresponds to that pixel. That's actually what I want, right? So I can't just look at the center point and do nice bilinear filtering. It's not going to give me the desired result. The desired filtering will give me the average value for all points that correspond to that pixel. So what I would like to do for my desired filtering is I need to know where this pixel corresponds to, this entire pixel corresponds to in texture space. And I would like to compute this average color in that area. Right. So this is what's desired, and we're not getting that. We need to figure out a way to solve this problem. What is important here is this dancing pixels problem, right? So we kind of need to figure out a solution for this. Does it have to be accurate? Maybe, maybe not. I don't care how accurate it is. I just want to get rid of these dancing pixels, right? So that's the most important component. These are flickering. That's the one that I want to get rid of. But computing this is not going to be cheap. It's not going to be cheap, because let me ask you, how many pixels do you think I have that how many texels of my texture do you think correspond to this one pixel? It kind of depends on how far the object is, right? So if the object is really, really far, and the object is so far that it's just one pixel, then my entire texture corresponds to that one pixel. So to be able to compute this average color, I need to look at all of the colors in the entire texture, which would be very expensive. It's a lot of work for computing just one pixel color. So way too expensive. We don't want to do that. So the solution to that is going to be pre-filtering. More specifically, a very specific type of pre-filtering is used for interactive rendering on the GPU. That is MIPMAPs. So here's how it works. Now, if my texture has just the right resolution, such that each one of my texels are on the size of a single pixel on the screen when I render them, then it's okay. So if my object is close enough such that my texels on that object are not too small, then things work out fine. But if my object is sort of far, such that each one of my texels are really, really tiny, then I get into trouble with bilinear filtering. So it starts breaking, right? So with MIPMAPs, what I'm going to do is that I'm going to generate versions of my texture that will have different resolutions. So at level 0, is going to level 0 of my mipmap is going to be the original resolution texture, and then with each consecutive level, I am reducing the resolution a little bit. So with this particular texture, I created 8 levels from 0 to 7. And with these 8 levels, I have different resolutions. At each level, I have half the resolution of the previous level. And I came all the way down to a single pixel. So this level 7 has just 1 pixel on it. And that 1 pixel contains the average color of the entire texture. So if it so happens that my object is far, far away and it just covers 1 pixel on the screen, I can just use this texture to look up the average color value. So if my pixel is not that far away and a little bit closer, then I can pick the appropriate resolution texture and use that. So that's the idea of mipmaps. More specifically, here's how this is going to work. With mipmapping, I'm going to look at this pixel in texture space. Look at this, but what I want is the size of that texture. I just want a single value that represents the size of that pixel, because I'm going to use that for determining what resolution to use, what resolution texture to use. So I'm not going to look at this funny shape of that pixel. I'm just going to treat it as like a box, all right, like an axis-aligned box in texture space. So this is the size of a box. So the separation between pixels should be around this size. So if this is also the size of a pixel, things are going to be perfect. So my bilinear filtering will give me just the right result that I want. Everything will be fine. I'm going to be happy. But if my texels are smaller than this, then I'm going to be in trouble. So what I'm going to do is that I'm going to look at my mipmap levels, and I'm going to pick the level that is closest to this size. Let's say that it is this level. Looks close enough? Okay, these texels look a little bit larger. Yeah, I'm displaying them as little boxes, but they're actually values at the centers. As you can see, it's a little bit larger than this, but close enough. So I can just use that. So what I need to do at this point is I'm gonna look at the center point of this position that I'm trying to compute, and then I can do bilinear filtering to get the result at that point, right? And if I do this, I'm going to get rid of this flickering that happened before, like the dancing pixels. But this is going to cause another problem. This is going to cause another problem because there is a discrete decision here. That is, depending on the size of this pixel in texture space, I picked a particular resolution. And at some point, let's move the object sort of closer to the camera, in which case this pixel area is going to get smaller and smaller. Or all of a sudden, I'll switch to another resolution mipmap level, which is going to have this sudden change from one resolution to the other, which is not going to be great. And also, this is not the perfect resolution that I want, because my pixels are a little too large. But my other next resolution has pixels that are a little too small. So what I want is actually something in between, which I do not have. But I can approximate it. So here's what I'm going to do. Let's say that this is level 5 that gave me the best resolution I have, which is not perfect, but that's the best resolution level I have in my mipmaps. So what is the next best? The next best is going to be one that is a little too small, right? Level 4, which is going to be a little too small. Level 5 is a little too large. So, and my pixel size in texture space sort of lies somewhere in between these two mipmap levels. So what I'm going to do is this. I'm going to do bilinear filtering at level 4 to get the bilinear filtered result for that position at the center of the pixel, right? I'm going to do the same for level 5. So now I have two different values for the same position in texture space. And then what I'm going to do is I'm going to linearly interpolate these results. And I'm going to linearly interpolate them based on how close my pixel size is to the separation between texels in texture space, or texel size, let's call it. So if my texel size, my pixel size is closer to level 5, I'm going to use more of level 5 and less of level 4. If it's closer to level 4, I'm going to use more of level 4, less of level 5, right? So I'm going to linearly interpolate between levels. And by linearly interpolating between levels, I kind of got rid of this discrete decision of which level to use. So I'm sort of smoothly going from one level to the next, to the next, and to the next. So I'm not going to see any jumps when I'm rendering. And this whole thing is called trilinear filtering, right? That this whole thing using mipmaps to do this filtering is called trilinear filtering because it's a bilinear filter and then another linear operation. Actually, two bilinear filters and then another linear operation, linear filtering, linear interpolation operation. Okay, so let's see an example. So here's an image rendered using bilinear filtering. Now, in this checkerboard pattern, I've intentionally chosen this texture for displaying this because even when the plane is now moving around, you can see that this filtering is sort of, there's something wrong with it, right? So I start seeing some strange patterns around here. You see that? It looks like the texture changes here, but it actually doesn't. It's just an artifact of bilinear filtering. Because I'm using bilinear filtering, this is what I'm seeing. But if I move this plane just a little bit to one side, all of a sudden this pattern here is going to shift and it will form a different pattern. So I'm going to have this crazy flickering that I showed you earlier. But even for a single image, this doesn't look quite right? So with mipmaps and trilinear filtering, I'm going to get this. So much better, right? So it was this. Now it's this with trilinear filtering. And the reason why this is happening is that let's pick a point here. That point corresponds to a pixel that's shaped, let's say, something like that. And that has a pixel, the texture space pixel size of this. And I'm going to be using that. I'm going to be using the average color that sort of corresponds to this blue area on the texture space. Yeah, I'm using bilinear filtering, but bilinear filtering is sort of approximating the colors of all the pixels for that area. It's not exact, but it's sort of approximating the average color for that area. Right? So that's the whole idea. But something happened here. If you're paying close attention, yeah, I got rid of those strange patterns that were forming here, and I probably got rid of all the flickering. That was the biggest problem. But I created another problem that's not that bad, but still bad. I created another problem, that is, I blurred the texture a little too much. I mean, you see, like, when you look at a distance, over here it's fine. As you look away from the camera, as the surface is away from the camera, it's starting to look blurry and blurrier, and at some point it just looks gray. And that's wrong, right? It's not supposed to look like that. And the reason why this is happening is because of this funny approximation here. Now, the actual shape of a pixel was something sort of elongated along one direction, because that's how I'm looking at it, and perspective distortion and all. And this is what it looks like. Actually, this is not related to perspective. Even orthographic projection can have this. But I'm looking at it from an angle. So this pixel shape in texture space is sort of elongated in one direction. And I approximated it using a box that sort of contains it, which is not a very good approximation. Right? So this extra bits around the pixel here cause this blurriness that is visible at distance away from the camera. Yeah, I'm getting something blurry, which is not desirable. So what can I do? Well, I would like to figure out a way to approximate this a little more accurately. And that brings us to anisotropic filtering. So anisotropic filtering is a method for sort of approximating the color value for this elongated pixel shape. I won't be able to do that by just doing pure trilinear filtering with mipmaps. Trilinear filtering is just going to blur it out. But what I would like to get would be something like this. I mean, it's going to be blurred along one direction, but I don't want blurring in the perpendicular direction. I just want to blur it in the elongated direction of the pixel. So I don't want this over blurred stuff, but I want some filtering, but only along that direction. And this is going to be a little more expensive to compute. Luckily, we can do that with anisotropic filtering using mipmaps. Here's how that's going to work. So instead of generating a box here, creating a box here that sort of contains the entire pixel area in texture space, I'm going to be generating a small box, actually multiple smaller boxes that sort of cover the corresponding pixel area. So more specifically, I'm going to draw a line along the direction of the elongated direction of the pixel, and I'm going to be computing mipmaps with trilinear filtering multiple times along that line. So in this example, I'm computing it 3 times. I compute it 3 times, and sort of it corresponds to a better approximation of the average color for that pixel. So it's not perfect, but it is a much better approximation than just using mipmaps with trilinear filtering, right? So with anisotropic filtering, what I'm effectively doing is multiple trilinear filtering operations using mipmaps, right? And by doing multiple trilinear filtering operations, I can provide a better approximation. And in the end, as you can see, comparing this bilinear filtering to mipmapping to anisotropic filtering, as you can see, I can get a much better texture filtering quality. Again, it doesn't have to be super accurate. I mean, of course, accuracy is something that's desirable, but we would like this to be cheap as well. So it's going to give us a good enough approximation of what the color is supposed to be, what the filtered texture color is supposed to be. All right? So this is the idea of anisotropic filtering. And as you can imagine, this is a lot more expensive. And this additional cost is directly proportional to how many times you're going to have to compute trilinear filtering when you're computing anisotropic filtering. All right, so how many times I need to do mipmap filtering to be able to do one anisotropic filtering. The good news is that our GPUs will do all of this stuff for us. So next time I'm going to talk about how to set it up. And you won't have to do much, basically. You will just need to tell the GPU, say, oh, I want to use bilinear filtering. And then you're using bilinear filtering. It's just automatic. Or you want to say, I want to use mipmaps. And GPU will generate all the mipmap levels for you if you want. And then it will figure out which mipmap level to use and then do the trilinear filtering automatically, and you won't have to do anything about it really. It's going to be all automatic. Same goes for anisotropic filtering. You just say, hey, I want to do anisotropic filtering, and that's it. GPU will do the anisotropic filtering for you. And with anisotropic filtering, you can also specify how many trilinear filtering operations that you are allowing the GPU to perform for each anisotropic filtering operations. You can specify the maximum number, because if you're really looking at a surface from a grazing angle like this, for each pixel may correspond to a very long line segment in the texture space, and that may require quite a lot of trilinear filtering operations to properly do anisotropic filtering. And you may not want that because that will be too expensive, so you can specify the maximum number. So of course, GPUs will have a limit to what that number can be. So all of this stuff, as you can see, we're using textures. As you can imagine, we're using textures a lot on the GPU. So all of this stuff is going to be completely automated for you. Now, the things that I'm not talking about as a part of this course is how to do this if you were to actually implement it yourselves. And that would be quite complicated because it's not that complicated, but it's sort of unnecessarily complicated because this is something that you're going to have to do for all of your renderings all the time. So it's much better to let the GPU do this automatically for us. If you were to do this filtering yourselves in your shader code, you can do that. But that will require you to compute the screen space derivatives of the UV coordinates, which is not a big deal because GPU can compute the screen space derivatives of the UV coordinates for you, the UV coordinates meaning the texture coordinates. The GPU can do that for you and give you the screen space coordinates, screen space derivatives, and the screen space derivatives will tell you how big that pixel is going to be in texture space, and if it's elongated in one direction, you will know along which direction it's elongated by looking at the screen space derivatives. Actually, fairly simple. And if you're going to do anisotropic filtering, you're going to have to do multiple MIP-MAP filtering. So that's going to be a lot of code, right? It's not too much code when you're just doing bilinear filtering, but when you add MIP-MAP filtering, it's a lot more code. If you add anisotropic filtering on top of that, it's even more. So just reading its texture value becomes quite a few lines of code. More importantly, though, that's going to be significantly slower than doing this on hardware. So our GPUs have dedicated hardware to do all this filtering operations for us. So not only we don't need to worry about it, but also it's going to be so much faster to do this on hardware instead of doing it in software. According to at least one estimate, it's about an order of magnitude faster to do this on hardware. So on the order of 10 times faster or something like that to do this on hardware. So you definitely want to use the GPU hardware to do this instead of writing the code in your shaders to perform this just texture filtering operation yourselves. Okay, but I'm going to talk about how to set it up and how to use these textures on the GPU next time. Today I want to end today's lecture with just a little more general discussion of textures. Now, when we talk about textures, especially in the context of interactive computer graphics, we think about textures that are supported by our GPUs. We think about raster images, like 2D images stored on the GPU. And I'm going to talk about that next time in a bit more detail. But the concept of texture is actually quite a bit more general than that. So texture is, in the context of computer graphics more broadly, is anything that defines a varying function on a surface. It doesn't even have to be surface. You can define it in volumes, you can define it in all sorts of spaces, but typically we render surfaces, so you can think about this as like texture is something that defines a function that sort of varies over a surface or over a domain. So you can definitely use raster images like 2D images for representing textures, but that's definitely not the only way of representing textures. You can use any kind of function to define a texture, and that's what we're going to call a procedural texture. A procedural texture can have a very complicated function or it can have a very, very simple function. For example, that checkerboard I showed you earlier, that could be a procedural function that's fairly easy to write. And I'm going to show you an example of that next time. You can write any kind of mathematical formulation in your shaders. So implementing procedural textures is at least theoretically possible if any practical problem is related to how much compute you're going to have to do to actually evaluate the texture at any given point. But other than that, your GPUs can do general purpose compute, so you can have procedural textures. But the other way of thinking about textures is that they don't have to be represented as 2D images. They can be stored in all sorts of different ways. And I'm bringing this up because this is actually a very, very important topic. Because as I mentioned in the very beginning when we were talking about texture mapping, we said we're not going to worry about specifying this mapping. We're going to say that, oh, somebody provided this mapping for us and we're just using that mapping that's given to us, which is great. We're dealing with a much easier problem just using a mapping that is defined for us. But if I give you a 3D model and say, hey, here's our 3D model, now define a mapping for this random 3D model to the texture space, you will see that that's a very, very tricky problem. It's not fun. Yeah, people spend a lot of time doing this. So as artists spend a lot of time doing this, researchers have spent a lot of time figuring out different ways of handling textures instead of just using 2D textures, right? 2D images. So as I said, a texture could be just a raster image, could be 1D, 2D, that's the one that we've been talking about, or it could be 3D, those are the ones that are supported by a GPU, it could be higher dimensional as well, or it could be a procedural texture. But beyond that, there are structures that are kind of like samples distributed over some domain, very much like these raster images, but they're not quite images. They're a little bit different. They're not 1D, 2D, 3D raster images, but there are structures that store this texture samples in very different data structures. So I did some exploration on that with two of my colleagues. We gave a course at SIGGRAPH 2017 on this, and then a follow-up paper, and then presented at Eurographics. Here, this is like a survey paper, and we're talking about different methods of different alternatives to texture mapping, just rethinking texture mapping. Different alternatives to texture mapping that try to address the problems, some significant practical problems of texture mapping in computer graphics. But the one among them that I like is my method. And there are very good reasons for liking that. That is called mesh colors. So that's the structure for storing the texture samples, but without defining a mapping between the texture space and this model space. Because a lot of the problems of texture mapping is related to this mapping and then defining this mapping. So it's actually, mesh colors that's designed to solve two sorts of issues. There are issues about what's called authoring, that is generating this mapping manually. And there are issues that are related to rendering, the problems that happen at render time because of the existence of that mapping. And mesh colors provide a way to eliminate that mapping completely by specifying the texture samples directly on this 3D model surface. So if this model is defined as a polygonal mesh, so typically what we use are quad dominant meshes, so either triangular meshes or quad meshes or quad dominant meshes that are combinations of quads and triangles. So with a quad dominant mesh, I can actually specify the positions of my texture samples like so. So I can, for example, in the lowest resolution case over here, I can have a color value defined at every vertex. And when you go to one higher resolution, now I have what's called edge colors. So these are vertex colors. Now I have edge colors over here. And you go to higher resolution, I have edge colors and then face colors that are defined at the centers of faces. And by doing so, I can form a structure that's not quite an image, right? It's not an image because it's defined on the surface of a model. But it also has the implicit mapping. The topology that I'm using for defining this mesh is what I'm using for defining these locations of these texture samples on the surface of my model. So this sort of simplifies the authoring process quite a bit, actually. It significantly simplifies the authoring process. And also solves a lot of the significant problems we have with texture mapping. Now, next time I'm going to talk about how to use textures regular textures on the GPU. And at the end of that lecture, I'm also going to talk very briefly about how to do something like this on the GPU with interactive rendering for interactive computer graphics. But I'm going to leave all that discussion to next time. I'm going to talk about the implementation related stuff next time. I'm not going to tell you exactly how to implement it, but I'm going to give you enough pointers for you to chase and figure things out on your own. That's the plan for next time. Yeah, so this is the stuff that I plan to cover for today. All right, let's end it here then. Thank you all for joining. Thank you. I'll see you all next time.